Okay, our first speaker, we are honored to have here Professor Carsten Bormann. He's honorary professor for Internet Technology at the University of Bremen. He's member of the board of its Center for Computing and Communications Technology, DCI. His research interests are in protocol design and system architectures for networking. He led the IETF efforts on integrated services for low bitrate needs, ISS low, and co-chaired the robust telecompression working group, enabling multimedia networking over low speed needs, wired and wireless, including internet telephony and IPv6 over low power wireless personal area networks working group. Most recently, he initiated the IETF work on constrained RESTful environments and the protocol, and is co-chairing the IETF core working group. He has authored and co-authored 28 internet RFCs, which are in turn cited 197 times in other RFCs. Lord, thank you very much.
Thank you. Good morning, everyone. I'm really happy to be here. I think this will be an interesting crowd. And I will be here for the next 48 hours. So those of you who want to catch me, you have 48 hours of time, then unfortunately I have to leave. I'm from northern Germany, so I'm used to a slightly colder climate and actually also more importantly to a flatter landscape, but I've made it up here, so you are lucky to hear me speaking today. So I want to talk about two things, and maybe a third if we have time. And I'm throwing over bottles the whole morning. So I really want to talk about the real Internet of Things. People have been talking about the Internet of Things for a decade now or slightly longer. And at some point we actually have to make it real. And we have to look at what's needed to make that happen. And in particular, I'm going to talk about standardization work, technical work that led to the components that are likely to make up the real Internet of Things. And if we have time, I'm also going to bring some layer 9 considerations. You know, the OSI model goes to the application layer, and then there is a financial layer, and then there is a political layer, and there are some political considerations. Maybe we can talk about management, security, and things like that as well. Of course, I have limited time, so we will only touch on each of these subjects. Now, this is supposed to be a lecture, but on the other hand, I really would like to get some input from you as well. You know, this whole setting with an elevated stage and a microphone and seating that is looking forward doesn't really invite people to asking questions. But please do. And more importantly, I already tried Frank at the end. If you don't agree with me, I really would like to hear about that, so I know what people to talk to after this lecture. So do interrupt me, just send up wave, and we can maybe have an interesting discussion. One more observation: the screen is pretty small. So those of you who are sitting in the last 3 or 4 rows, there are wonderful chairs up here in the front, and I really invite you to move forward. And I'm only going to continue until at least one person has moved forward. Okay. Yeah, I'm not exactly known for slides that can be seen from So, all of you probably have seen this slide or some other version of it, where Ericsson points out that in the history of the company Ericsson, they spent more than the first century mostly about connecting places. So there were phones from one house to another house, from one house to another desk, and so on. So the first thing they did in the history of the company was connecting places. And of course, in the history of the internet, the same is true. We are still talking about internet sites as if these were something that has a locality to it. And then at some point in the mid-80s, we started to think about more about mobile technology. And the result is that we started connecting people. And it turns out that there are more people than places. So this generated, first of all, a nice economical boom, but it also changed the way we are using the network a lot. And what we are seeing now is that we are moving to connecting things as well. Of course, things have always been on the internet, but now it is becoming more natural for a thing to be on the internet. So for a while it has been pretty normal to have something like a printer on the internet. Things have been on the internet. But washing machines and toasters and so on, well, some people have always been doing that, but it never has been a mass market. So there are some numbers here. 1 billion places, 5 billion people, 50 billion things. The absolute value of those numbers is not so important. The important thing is we are massively scaling things up. And there is an IDC study talking about 220 billion nodes by 2020. Let's see how that turns out. But the important thing is we are getting a lot more nodes. That's not a big problem for the internet itself, because companies like Cisco want to make you believe you have to upgrade your network to carry all those traffic, but of course a single YouTube video consumes more bandwidth than 1,000 washing machines. So that's not the particularly interesting argument. But the more interesting observation is somebody has to buy all those nodes. Somebody has to pay for them. So we actually have to scale down the nodes to make the whole thing affordable. We have to make sure that we can attach connectivity to things that aren't particularly valuable. And also, of course, we want to attach connectivity to things that aren't that big. The washing machine, it doesn't matter if you put a desktop computer into a washing machine. It probably will rattle apart at some point. But there are other things that are very small, and these need small nodes. So scaling down actually is the more interesting aspect of the Internet of Things. So we have to scale down the cost of those nodes, and to be able to do that, we have to scale down their complexity. And that's something that computer scientists historically have been really bad about. We don't know how to catch, rein in complexity once we have unleashed it on the world. We make things ever more complex. We add another layer on top of what we already have. And we have to stop doing this if we want to generate the real Internet of Things. There are a couple of terms you may have heard in your childhood and you may have forgotten. For instance, the cent is a really important thing in the Internet of Things because that's the unit of cost. We're not talking about dollars or kilodollars here, we're talking about cents. And we're talking about kilobytes of memory. So I have a generation of students who never actually learned what a kilobyte is. They know what a megabyte is, they know what a gigabyte is, but they have absolutely no connection to the idea of a kilobyte. We have to get back there. And we have something called a megahertz, which is the speed of those things. Not just because it's cheap technology, but also because it's supposed to use less energy. So there's a bit of a shift going on here. And when we talk about constrained nodes, we are really talking about devices with certain orders of magnitude. And we have spent a couple of years finding out what orders of magnitude we're actually talking about. And in the end, we actually got an RFC that discusses this in a little bit more detail, RFC 7228. There is, of course, a spectrum. There are devices that are really easy to put on the internet, like my laptop. There are devices where it's a little harder, like my phone. And so on. And there are devices where it's difficult, but not particularly so. And there are devices where it's becoming more difficult, and then there are devices that are so constrained that actually it's a heroic act to get them on the internet. And you probably cannot build the Internet of Things based on heroic acts. So we probably have to focus on devices in these two classes, and of course larger devices where it's worth putting in more functionality. We can do that, of course. But class 1 and class 2 devices, where class 1 is defined as about 10 kilobytes of RAM and 100 kilobytes of code. And class 2 is maybe 50 kilobytes of RAM and 250 kilobytes of code. That's about the size that we are talking about when we really want to have 50 or 200 billion of them out there. I think that has to shape our thinking. And in particular, we actually have to do a lot of work to get this class 1 world online, because without fixing the protocols, it becomes a heroic act to get them online. And of course, we also always have to think about energy. So that's, most of you will know that that's one of the things that really is different in the Internet of Things. So, with respect to the timeline of technology, does anybody in this room know what this is? Well, some people here have gray hair, so they should know that. It's a PDP 1134. It's a photo taken in 78 or 79. This is actually the CPU here. These are just peripherals. So this CPU has approximately 64 kilobytes of RAM. Doesn't have quite as much code space as a class 2 device, but it's kind of the computing environment that we are interested in here. So we have to shrink this thing into the small devices. Okay, 35 years of Moore's law is going to help us doing that. But there's something peculiar about Moore's law. In the Internet of Things world, Moore's law only barely applies, because all the savings we are getting from Moore's law, everything that is getting better from year to year, is going into lower power and lower cost. It takes a lot of time for Moore's law to actually give us more performance, more ROM, more RAM. So most of the surveys we did in 2004 about available chips are still mostly available. We may have doubled since 2004 in the amount of RAM or flash that is available in low-cost chips, doubled in 10 years. So don't rely on Moore's law. Moore's law is not going to help. It's going to help you a bit, but it's not going to just take all these problems that we are working on away. At least not if we want to scale up massively. Okay, so this is about the nodes, the networks. Probably most people here have a pretty good understanding of the network issues. To be able to be power efficient, nodes must sleep a lot. So we're talking about hundreds of microwatts as the sustained power that is available to a node. We're not talking about 5 watts or 2 watts or something. We're talking about hundreds of microwatts. And we're talking about networks that maybe have a couple hundred kilobits per second raw data rate, but do so with high loss, high link variability. So it's somewhat hostile environment. It's not that easy to get things going in this space, and the radio environment also is unstable. There are also some limitations, like packet sizes and so on, that make working with these things different from working with, for instance, Ethernet. Most people have grown up on Ethernet these days, and Wi-Fi has deliberately been made look like Ethernet. So even people who are using Wi-Fi really think that they're using Ethernet there. And these networks are different. Now, when I talk to people about Internet of Things technology, I'm always talking to two camps. One says, IP is too expensive. I cannot use IP. I need to use Bluetooth Low Energy and put my application data right on those 27 byte packets, and then it barely fits, and we can make things work. So that's one camp. My hand-knitted protocol is better than what I can do with it. And the other camp is, well, people have been putting web servers on PIC chips for 10 years now, so what's the problem? The internet protocol just works, we can just use it as it is. And the interesting thing is, of course, both camps are right. But that doesn't help us in creating a network that has a lot of opportunities for connecting sensors and actuators to intelligent nodes. So what we actually have to do is address the needs of both camps. So this camp actually wants to have very efficient protocols, and sometimes they are actually clamoring for efficiency in places where it's not that important to be efficient. So there, apart from the technical problem, there's also a cognitive dissonance problem. If you're using 1 byte more than you have to, some people just opt out and say, no, we cannot use 1 byte more, even though it's maybe a reasonable trade. On the other hand, we have the need to integrate as much as possible with what's out there. So we don't want to throw away the network effects that we already have from the internet. So it's really important to get those who have interesting things going on board in the database. But above all, IP is just a very important component here. If you look at other industries that have been completely transformed within the last 20 years, it's very obvious that the driving factor actually was getting more things connected to each other in a less complicated way. And IP is doing exactly that. IP is not the internet protocol, IP is the integration protocol. It happens to run the internet. Now, IP is turning 40 this year, if you count the original self-count paper. So it has collected some baggage. And one question is, do we need all this baggage in the Internet of Things? And we have several opportunities to get rid of baggage. For instance, using IPv6 instead of IPv4 lets us get rid of some IPv4 baggage. There are some people who are going to say, well, we don't really need it, but it's there and it's easier to not get rid of it. I think that the question really we have to ask ourselves is, do we want that baggage to be around? Is it a reasonable trade-off to have complexities that come from a different age weigh us down? So I think that there is a pretty nice illustration of that question. I mean, can I use asymmetric cryptography on a class 1 device? Of course I can. I also can transport sofas with motorcycles. It can be done. There's no question about that. But do I want to do it? That's the interesting question. And the other interesting question is, when I am choosing my mode of transport, when I'm deciding whether I'm going to buy a truck, a car, or a motorcycle, is it important for me to be able to transport sofas or not? Because I'm probably going to buy a truck if sofas are really important for me. And maybe it's a good idea to actually, even though it can be done, to not do it. So this is the kind of trade-off that we have to do. And a couple of years ago, I gave a talk at the IETF plenary entitled Garrity and Fluff, which is really trying to summarize the problems we have with the existing internet protocols. So garrulity means somebody is excessively talkative. If you think about what a Wi-Fi node does when it wakes up and talks to other nodes and so on. But there's really not a need to do all this talking. It's not necessary. It's just it's certainly friendly to the rest of the network and so on, but it's errors. And the other thing that has accumulated is a lot of lint, a lot of fluff, and that's the other part that we want to get rid of. And there are good reasons for that. So this is just a random graph from a random paper that I had available. It shows the energy cost for certain kinds of processing, and in this case it's cryptography. Well, there is an AES going on, there's a skipjack and a CMAC is being calculated and so on. And then we actually transmit the packet. And you see transmitting that packet and actually receiving the packet as well. This is a little bit anomalous here. These are the expensive parts. We really have to look at the number of the packets that we send and receive, and these are the important things. And a little bit of processing. Of course, you want to minimize processing, but that's not the problem. You really want to stop these devices to talk to each other, etc. when needed. The other thing, the fluff thing, is really about thinking about complexity in new terms. So I already said this class 1, class 2 thing. When we talk about code complexity, normally when I'm designing an internet protocol, I think about code complexity as a barrier to implementing things. Somebody has to sit down and write all this code, debug all this code, operate all this code, and so on. All these things are still valid in the Internet of Things, but also we have to fit it into the limited amount of flash memory that we may have available in our nodes. So there is a significant additional cost to complexity. And keeping things simple is not just good engineering here, it really is a significant cost. So this is about code complexity. There is also a state complexity, and with respect to RAM, our small nodes are even more constrained. So we really have to think about state, and we also have to think about bounds for state. How can we actually make sure that the state we need during the life cycle of the device never exceeds the amount that is available. Packets are expensive, I talked about that. Listening is actually also an expensive thing. If you're power constrained, then listening is almost as expensive, or for some modern radios actually more expensive than talking. So you have to think about when you want to listen. And one thing that follows from listening being expensive is that the old idea of using the unhindered propagation of radio waves to do multicast suddenly doesn't work anymore, because everybody is sleeping, nobody is listening, and so multicast goes into thin air and into nodes. So we have some things that we have to do to control the complexity. And when you look at these numbers, you always have to remember this is not just the operating system, the networking code, the security code, the device management code, the firmware update code, and so on. That maybe actually is an application running on that node, and that also needs code and state. So it's not sufficient to have a version of Contiki that somehow fits into a class 1 device. You actually want that node to do something useful, and so you have to save some space. So talking about the two camps again, this is kind of a map of the Internet of Things world. So this is a barrier. There is a part of the landscape that simply cannot use Internet technologies because the complexity that is acceptable or the energy that is available is just too limited. So if I have a light switch that is activated by the energy of pressing that light switch, we don't know yet how to put that onto the Internet. We have some ideas, but I don't think a commercial product could do this in the right way. So this area here exists, and this area here exists. And also looking a little bit further, when I can spend more money, when I have more energy available, when I can put in more complexity, actually I can use internet technologies unchanged. So I can have a light switch that uses HTTP and XML and SOAP and all this stuff. And even further along, I might actually have an application where I can just go ahead and put in a Raspberry Pi and be done with it. So this is the $40 mark on this graph. And well, $40 by 50 billion nodes, that's $2 trillion. And it's not quite clear that people will pay that amount for the thing. So we have to go left on that scale. And the work that we are doing is about moving this boundary to the left. Now I drew this boundary a little bit wide because, again, we can put lots of engineering, heroic measures into something, and then you can make it work with a little bit less complexity and so on. But there's not really much you can go there by investing lots of money. And of course, the fledgling market really doesn't want to invest lots of money just to reduce complexity. So we have to change protocols to move this barrier, and so we get this new space here, the gray space that we actually can address. In the total scheme here, the gray space may look tiny, but you have to remember that the cost is going down here from right to left. So the number of devices I can actually have is going up a lot, and going from this point to this point in that curve actually is a significant difference. So it's actually important to do this. How can we do this? Some protocols can be fixed. So for instance, the IPv6 neighbor discovery protocol definitely never was done for an Internet of Things kind of environment. So we just took the protocol, which we are lucky is sufficiently modular that we could replace parts of it and do something called 6OpenMD. I'll talk about that a little bit more. And everything else stays as it is. This is also a local change. It doesn't impact the guy at the other end. So it's something that can be done with a limited amount of engineering. Sometimes we can just use an existing protocol and simply remove a source of complexity. So if you look at something like DTLS, the data-driven version of TLS, the SSL protocol, when you look at the code complexity of implementation, most of that actually is in the X509 certificate handling code. So that is larger than the whole rest of the system. And by getting rid of X509 certificates, that problem can be reduced significantly. Sometimes that doesn't work, and you actually have to redo things, but you can still maybe reduce the architecture and build things in such a way that things can interact. And that's what we have done for HTTP, which has lots of package and also lots of deployment that we have no chance whatsoever to change. So there is little point in trying to change the rest of the HTTP world for the Internet of Things. So we just did an equivalent. I'm going to talk about that. And that is more appropriate, but it also meshes in with the existing HTTP, so those protocols work well together. So the kinds of changes we can do are local changes, changes that only happen on the Internet of Things side. So if we have an Internet of Things side talking to a traditional node on the Internet, the traditional node doesn't know that we made that change. We have end-to-end changes, where both sides actually have to change. And we have global changes, where everybody has to change. And obviously, those global changes never happen. So there's very little point in trying to do a global change. Changing every router on the internet is not something that will happen very quickly. So we are trying to keep changes local, or if there is a good incentive for the other side to actually follow suit, to just do an end-to-end change, but never do a global change. So we're not going to change the IPv6 address to make the Internet of Things. Yeah, that has to stay as it is because it will change every. From an engineering point of view, there are also single-layer and cross-layer changes. That's typically much less important than this part. It does become important when different organizations doing an implementation have to work together to effect a cross-layer change. So, for instance, if in an organization I have to get application programmers and firewall managers together on a table to get something done, that becomes more difficult than if just one of them does something. That's why applications develop technology for certain firewalls and so on. Now, one thing that I haven't said in the first 25 slides here is sensor network. And I'm going to try to not say it after these three slides. This is a dark slide because it describes a dark reality. So we have been trying for a decade to be unlike the internet. And certainly there are good motivations to do that. There's always good motivations to do good research, of course. There are hard power constraints, device constraints. It's also interesting to discuss distributed data processing. Sync-oriented computing is an interesting idea. There are lots of things that we need to be doing in the self-X space, and of course localization and timing does need additional support. So this is all good research, but it didn't really help us very much on the way towards the real Internet of Things. We now have a lot of Lego bricks lying around, but we still have to build the castle. While I'm criticizing the research, I have to have this slide in every talk I give. Who of you knows this paper? Okay, everybody else, after this talk or in the lunch break, please rush and read this paper. It's from 2005, it's now also almost 10 years old. And it is about research in an adjacent space, in the money space, in the mobile ad hoc network space. And there are lots of people doing research there, doing simulations. And most of the papers published there are just garbage. And I'm not talking bad about them. Just read this paper and you will know what I mean by they are just garbage. So don't make the mistakes that have been documented so nicely for 9 years in your research. And unfortunately, much of the sensor network research hasn't picked up that message yet. Anyway, so we are not going to do the classical wireless sensor network stuff here. And apart from the fact that it's always kept very hush-hush in Europe, that this is mostly motivated by military applications, the problem here mainly is that a systems approach, where we design everything from scratch so we can optimize every single component just for this one specific task that we are addressing, that doesn't lead to integration. And one thing we have learned in IT for the last 50 years, integration is really what drives technology forward. So if you cannot integrate, then your technology probably is not very useful. Okay, so terminology, quick slide about terminology. Internet of Things is not exactly my favorite term for what we are discussing here. My only problem is I don't have a better one. So I'm going to continue using it. In the 6th patent book, We call it the wireless embedded internet. The rural people are calling it low power lossy network, which is completely missing the mark, but okay. IP smart objects is a pretty good term, but it's rather inaccessible to people without a technology inclination. So let's stick with Internet of Things, but let's not try to over-interpret this term. It's really about increasing connectivity, getting the digital and the physical world together. Cyber-physical systems. I forgot to put cyber-physical systems there, sorry. Okay, Internet of Things officially now is at the top of the hype cycle. You know this hype cycle thing where something gets an innovation and is talked up and up and up, and then there is a peak of inflated expectations, and then there is a valley of disillusionment, and then at some point we find out how to actually use it. And according to Gartner, in July, the Internet of Things was at the top of the hype cycle. So the next thing that will happen is this valley of disillusionment, because people will notice that what has been hyped is not exactly what we need to realize. So there will be some realignment, some readjustment. This is a published paper by Gartner, so just Google Gartner hype cycle and you'll find it. So when I talk about the hyped Internet of Things, this is really a number of benchmarks here. So the hype IoT uses IPv4, uses nets, does complicated things to go through nets. So this generates a lot of complexity that we don't actually need in the Internet of Things. In the real Internet of Things, we are getting rid of this complexity by simply using IPv6. The hype Internet of Things is completely oriented towards device to cloud, because all the business models try to make use of data that are collected by those devices in cloud applications. So in the hype Internet of Things, you will have devices talking to the cloud. We have time, I can say some more about that later. In the real Internet of Things, we have an internet, so nodes can talk to each other and not just to the cloud. So devices can possibly exchange data without surrendering them to some cloud application. Because everybody is doing their specific business model in the hyped Internet of Things. We have lots of silos, while the real Internet of Things is all about this term from Dave Weinberger, small things loosely joined. So if in your architecture pictures you have this big thing in the middle and everything connects to it, you may want to think about what you are doing. Well, maybe you are building the CompuServe of the Internet of Things. But this is maybe a useful transition of technologies. In the end, we want to get rid of the CompuServes and the AOLs and build an actual Internet. Much has been said about security. Most of the hyped developments have very, very questionable security. I mean, security of the kind where security person looks at it, shakes the head, and goes away without saying anything. We need real security. If we have 50 billion things out there, which are recording everything that's going on in our lives, which are controlling a lot of things that are going on in our lives, we want real security. And this will never happen without real security. So this is one difference. Then I talked about this $40 boundary. Does anybody here know an Internet of Things device that costs less than $40? I don't know. And we really have to get to a cheap device. So there is about an order of magnitude that we have to skip here. And as I said, Moore's law is only going to cost so much here. We have to think about good ways to reduce the complexity in order to reduce device. And finally, when you look at those current devices, what is their power consumption? They give that in watts. And they should be giving it in milliwatts or microwatts. A recent study by a German company showed that to install all the energy-saving things that they had invented increased the static power consumption of a household by 14 watts, which is a little bit more than the energy-saving stuff saved. So we really have to make sure that we go from there to there, and again, we have to control complexity. Okay, this is my first take-home slide. I'll give you 2 minutes to come up with questions here, so we maybe can have a little bit of a discussion. And then I will run through some 100 more slides and set an attitude. Use the opportunity and try to create some questions. Yes.
He thinks that real security and the cost of the power consumption are two requirements that can be coexistent.
Absolutely. So the question is, I had some slides later on how this might be done. The question really is, do we have to put all the security that is needed for an application into a single device, or can we distribute responsibilities between different devices, some of which are higher power, less constrained, and only operate when we actually do those things, like setting up nodes and so on. And then after that, a node may be able to run for years without running, for instance, any asymmetric cryptography. But this has to be worked on, because the internet right now doesn't work that way. The internet right now does a lot of expensive security for every single transaction. Yes?
How much time it will take until we arrive at having devices with the cost smaller than $5? Just because, as you said before, that Moore's law is not the good thing to be applied for calculating. So how much time do you think will take until we get there?
Unfortunately, Carol, who said is only coming on Thursday. You probably should ask him.
Okay.
Carol from the OpenNode project. So they right now have a pretty interesting hardware platform that has a chip on it, which costs $4.
Okay.
But of course, it does cost to manufacture the development board. So we are on the brink of getting there. It's not like it's impossible right now. Maybe the hard boundary of $5 will take some more, but going below $10 is already possible. So we're getting into light bulb territory, into genuine light bulb territory. But we have to be very careful what we put in.
Do you think that the cloud-based infrastructures will be out of the Internet of Things business model in the future?
No. I think the cloud is needed for many reasons, because people want to store data there, because some analysis can be run in the cloud much better, because it's a good way to provide good user interfaces and so on. But the important thing is to give the cloud a place, not to say the cloud is the architecture, but to say there are some things that happen in the cloud, there are other things that happen between the devices. Yes?
You said that multicast is a bad thing or didn't work. It's only partially true. It's true if you assume Contiki Mac, for example. Because in Contiki Mac, you will spend all the time between checks for transmitting. But if you assume other Mac layers, you can implement multicast downstream in in the correct way. So can you comment on this?
Yes, so there are MAC layers that are particularly multicast unfriendly. So if you have a more multicast friendly MAC layer, let's say Wi-Fi. Wi-Fi does some work to enable multicast. But still, if you look at what happens in Wi-Fi, is multicast is way more expensive, it's a much larger error rate, a much lower bit rate. Because there are just some things about multicast that are difficult to transport from the 1970s radio technology that most people have in mind to what we have in radio technology today. And I'm just talking about the radio layer. Now, on top of that, of course, we have to think about things like layer 3 protocols that do the forwarding of the multicast. And in a network that is very much in flux, it's very difficult to do this. So there are some protocols now, like the Ripple protocol, the multicast. I forget what the application is for, but the thing that comes with Ripple, that actually provide a limited form of multicast, not IP multicast, but a different model of multicast, using flooding, which may be useful for some applications. So I'm not saying multicast is bad, I'm saying the assumption that IP multicast is there, is cheap, like it was for Internet, that is bad, because it makes you design systems that use lots of energy, lots of complexity for running these multicast protocols, which could be done much easier. Frank?
Yes, I just wanted to say, in the context of a pure city, smart city or city, you have the price of your sensor, but a lot more important is the price of installation and maintenance of that sensor. So if you say that $40 is too much, you can also conclude that in cities we will never find a lot of sensors, because to maintain a sensor, the cost is at least 3-4 times higher.
But it still helps even with the total cost of ownership if your sensor is cheap, because they are much easier to maintain when they are cheap. You can throw them away, for instance. I think it's important to think about the cost of the device. It's also very important, and that's somewhere between this security point here and this point. It's also very important to talk about the life cycle of devices, how we can get the processes that make those devices become part of the network and maybe be taken away from the network at the end of the life cycle, how to make them more streamlined than what we have today. I think that's important. Yes, I think electrical socket is about $40 in installation cost, average for a large number of buildings. So we will never get below that if you look at installed things that need wires and so on. But there may be other things where it's just nice to be able to drop things somewhere and forget about maintenance, because if it's gone, just put in a new one. Yes?
I have two questions. One about the cost. Do you think that the devices that we can find for €40 or $40 or more cost really about 10, and the rest it is just enterprise that wants to make some profit? Say it's incredible. That is why you must pay this price.
The cost of the device is the bill of materials, the cost of production, and the cost of engineering. And right now, because the production runs are so small, the cost of engineering dominates. That is going to change. But still, we have to get the other two components under control, or there's no point in reducing the cost of engineering, because the whole thing will stay too expensive to get large production.
Second, about the first line, I think in this case, if we talk about IPv4 with NAT or IPv6, to go towards real IoT, we must proceed in new terminology to global changes, because a lot of service providers for particular people, like me, for example, at my home, offer to me only IPv4 address. So, do you think it will take a lot of time to change the mind of service providers to completely go towards IPv6?
There is a little component of betting going on here, which is that the IPv6 migration is faster than the Internet of Things migration. So if that is not true, we have a problem. I certainly agree with that. But people consistently have overestimated the speed with which IPv6 was rolled out since about 2011 and have underestimated it since 2011. It's going into networks, and I live in a country where more than 10% of the people already have it in their homes, and it's going to get better in other places. So, yeah, sometimes you have to make compromises, and so a product that has to go to market this Christmas will have to do something about IPv4. I agree with that. But this is not going to be the product that really will transpose real internet.
And do you think in 10 years it will be completely
Yes. Talk to me again in 2024. Okay, thank you for a little bit of introduction. I was hoping to get a little bit of discussion going here. So let me move into the technology, and doing that, I'm probably going to talk mostly about the IETF, because the IETF is the standards body that actually makes many of those things work. And this is not trying to slide IEEE or other bodies that do wonderful radio work. For instance, radio work is absolutely necessary, and it's a big technology drive that pushes us forward. But again, in the end, we need to connect things. Now, the IETF actually has been working on the Internet of Things since 2005. So 2005 was the time of the creation of the first working group that worked on the Internet of Things subject. And right now we have 7 working groups in the IETF that work on this. 3 on the network layer, 1 routing working group, 1 application area working group, talking about application protocols, 2 security working groups, and maybe we will get an 8th working group at some point that will discuss management, device management. So if you don't want to wait for that, there are other people working on device management, like the Open Mobile Headset Association, or they have a great scheme for that. Okay, so this is actively being worked on, and there are a number of RFCs out there. Let's just step through the layers here. So let's talk about network and routing first. Well, I probably don't have to tell you about the end of IPv4. This is a now 3.5-year-old picture showing the ceremony where the last IPv4 addresses were headed out to the regional registries, so to currency and the other registry heads. And depending on what part of the world you are in, the time when the addresses will run out is different. So Africa still has a little bit of time, and everybody else is a little bit in crunch already. And we know IPv6 has enough addresses. And well, this is an old, really old slide from me, where I was trying to make the point that it's not useful to use IPv4 for things that are produced in quantities per year that approach the number of IPv4 addresses. Okay, so that was my IPv6 pitch. That work has happened, but we needed to complement it to make it really useful for IPv6, for the Internet of Things. And to do that, that's the typical IETF approach. We're not doing this in general terms. We pick one technology and make that technology work. And in this case, we focused on IEEE 802.15.4, better known as ZigBee. ZigBee is a brand for specifications that includes 802.15.4. Well, it's pretty popular, measured in the number of chips that are available out there. And I think most of you know it, so I'm not going to say very much about it. One interesting thing is it only has up to 127 byte packets. So to map IPv6 onto it, we have to do some work. And also that there is no good support for multicast in that backend. So we built a working group in 2005. By now, that actually has been dissolved. The IGF has the habit of dissolving working groups after some time. So this doesn't mean that the work is over. There's a new working group actually doing that work with a slightly different charter. And relatively quickly, we did the encapsulation work. So how do you represent packets relatively efficiently? That also had some initial header compression work, but we threw that away later on because of changing requirements. We solved the fragmentation problem. IPv6 has a 1280 byte minimum, maximum transmission unit, minimum ATU. We discussed mesh forwarding, but never quite got that to work. And in particular, we decided to use as little of the MAC as possible. And that helped vendors who didn't want to run the whole relatively complex MAC protocol, but it also is the foundation of the success of 6LoWPAN as a technology for other radios, because it never got dependent on 15.4. So what did we have to do? Encapsulation needs some form of packet identifier, so we defined a way to identify packets. We defined a way to compress IPv6 headers down to a very few bytes. I'll talk about that in a minute. We defined fragmentation, so a way to take apart a large IPv6 packet into multiple MAC layer packets. So this is all there, was all defined in 2007. This was done, completed, published a year before David Keller and Jonathan Witt published their big call for making the real Internet of Things happen. So after some deployment experience, we found out that the header compression scheme in 4944 wasn't very good. So the next thing we did, we reworked that. Header compression is a really complicated issue. And it's interesting because if you look up header compression in Wikipedia, it doesn't even have an entry. But it's a science that's probably known by about 10 to 20 people in the world. So the existing header compression schemes are all flow-based because they have been designed for compressing phone calls. If you have a phone call transporting FTP packets, you have lots of packets that are similar to each other, and it's easy to compress those. That's not the kind of traffic we have in Internet of Things devices. We don't have closely spaced packets that look similar. So we were trying to go stateless, but that didn't work very well because if you don't have state to work on, there's not much you can compress against. So we came up with something called area context state. So for Internet of Things network, for 6LoWPAN, we can define area context state and compress against that. And that means that from a 48 byte combination of IPv6 and UDP headers, we typically get something like this, which may have 2 bytes for IPv6 and 4 bytes for UDP in the best case. That's when everything lines up. It can be larger, of course, for instance, if a device is being addressed that is outside the current network, then of course you have to add some addressing information. So this document, RC6282, goes into considerable complexity. And I'm not showing this for you to understand it, just showing we have some complexity here. We have a 16-bit header that controls how this compression is going on, and part of this header is doing addressing, and parts are addressing other components of the IPv6 header, and so on and so on. So I'm just leafing through these slides to leave you with the impression there is some complexity here. And I was really trying to convince you that we want to minimize complexity. So there's a little bit of cognitive dissonance here, and it goes on. We actually have a current draft right now, the generic header compression draft, that also defines compression of other headers, for instance, the Ripple, the routing protocol headers. And so we will even do some more work there. And this is a simple XZ77 compressor, so it essentially finds redundancies in the payload. This is a static dictionary and parts of the IP address, and you essentially can back a reference into previous parts of the payload or the dictionary, and this way it gets a compression factor of between 1.65 and 1.85. So this is all a lot of work, a lot of complexity, but this is something we probably have to do, because the overhead of an uncompressed IPv6 header is just too big. 48 bytes for IPv6 and UDP is too much. If you think about Bluetooth Low Energy, that only has 27 byte payload sizes, it clearly doesn't make a lot of sense to send 2 packets to just send the header. Data. So this is complexity that we had to incur. This is also local complexity, because it only happens in a device implementing 6LoWPAN. So as soon as the IPv6 packet escapes the 6LoWPAN, goes into more traditional networks, nobody notices that this was going on. So in the end, it was a reasonable trade-off to do this, and it takes away one of the major arguments against the Internet of Things. The IP headers are too large to use them in our tiny networks. Now, I talked about neighbor discovery as being a protocol that needs to be fixed, and that's the other part of the 6LoWPAN work. And the first thing we had to fix was the entire model. In IPv6, normally if a host enters a network, it talks to a router, gets a prefix from the router, and then it's in the network spanned by that router. But when it changes to another router, it probably gets a new prefix. And that's not a very useful scenario for, say, a home network, where depending on whether a door is open or not, the device may be talking a smoke detector or the washing machine or something like that for its routing requirements. And it doesn't make sense to give it a new address each time somebody opens the door and closes it. So what we did was we did an addressing model that actually has a subnet that is larger than the links spanned by every single router. So devices can move from one router to a different router and maintain their address. That's really the major thing we did. And the other thing was we got rid of most users of multicast. So the idea, this is something that is still a little bit in the future. We cannot quite do that yet, missing one field. The idea is that we might have something like a Wi-Fi or Ethernet link where multiple edge routers are connected to, and those edge routers continue this link into the constrained space, and hosts really are pretty free to move in this area. Right now we only can support one edge router, but there will be support for multiple edge routers. So we can do this, and this is the work. Technically, that was a pretty straightforward. Once we had decided what we wanted to do, this was a pretty straightforward thing. We just had to define a few more options for the neighbor discovery protocol. Those were standardized in 2012, so this also has been out for a while. And the typical exchange now looks like this. So when the host comes up, it finds a router. That's the one place where we actually can use multicast, because the point is to find someone who's in your radio vicinity. So that's where multicast actually works. The host gets a router advertisement. This is the standard IPv6 stuff. And now, instead of doing all this MLD stuff and so on, we just do a special label solicitation with this option, the address registration option, and that can also be forwarded in the form of duplicate address resolution towards the edge router, and that's, for instance, used for the 216-bit address on the 16. So, in summary, really, what this does is it uses one principle, which is there may be less constrained nodes somewhere in your network, and use them. Don't try to do everything within the constrained node. Make use of the less constrained node as much as possible. So, for instance, the duplicate address detection runs on the edge router, not on every single router out there. Only the LBR needs to have this list of devices that are in different software. And the LBR also is a logical candidate to do that, because if you remember the architecture, the LBR is the edge router is the one that has the other connection into the backbone. So it already probably needs more power than the other devices. So it's a logical thing to also design that work to the edge router or LBR. Okay, so in summary, the other half of 6LoWPAN was fixing the addressing model and getting rid of some fluff. I'm sure Steve Deering would not agree with me that IP multicast is fluff, but the way we have been building the architecture on top of IP multicast is a problem, and that has been addressed. Interestingly, the Ethernet people are now looking at 6LoWPAN NP and defining something called efficient NP, which essentially uses the same options, but also needs backwards compatibility, which we didn't need to address. Because NP actually doesn't work that well on the Internet either. So that may be something that flows back from the Internet of Things environment and reduces complexity in the big Internet as well. Okay, so this is 6LoWPAN. This is pretty much a done deal. This, of course, doesn't mean that there is nothing to do anymore. Again, as I said, we want to do multi-attached networks. But people have been picking that up. So, for instance, there is now a ZigBee IP. Again, ZigBee is a brand, and one of their branded specifications is pretty much 6LoWPAN. So the 6LoWPAN adaptation layer is in there. Sorry for the colors. And there have been interoperability testing events and so on. So this is done, but can be made better, of course. Interestingly, this is now also getting some traction outside the 802.15.4 work. So the Bluetooth people have this extension called Bluetooth Low Energy, and or Bluetooth Smart. It's a marketing name for Bluetooth Low Energy. And they have picked up 6LoWPAN and put it into their specification. That actually was completed in the 6LoWPAN working group, but then the Bluetooth stick backpedaled a little bit, and we are now in negotiations with them and getting this work done. The Z-Wave people have done a specification based on 6LoWPAN. And the ultra-low energy DECT people have done specification. Now this is an interesting technology here, because there is a DECT chip in almost every single home gateway that is being sold right now. So there are 250 million DECT chips out there, and many of them can do that already. So it would be a software upgrade to get that available in the home environment. And it's dedicated spectrum, so it's an absolute green environment for getting a reliable home-based Internet of Things service going. So this work is no longer done in the 6LoWPAN working group. There is a new a version group called 6 low, because it's not just about wireless personal area networks, it's for using 6 in low power, low something networks. And the current agenda includes PHC, the generic collaboration, and MIB, of course, we have to do some work on management. We talked about good local energy, low pan on Z-Wave, DECT. There is one guy who is using BACnet hardware and some part of the BACnet specification. BACnet is a building automation bus based on twisted pair wiring in RS485. And the idea is to just run 6LoWPAN on RS485. So all the things that make 6LoWPAN useful in a wireless environment also can be useful if you have a limited speed environment like RS485. Low-speed powerline communication is getting 6LoWPAN, and the newest route, some people from H3 are looking how to actually do 6LoWPAN over NFC. So when you have an NFC communication being set up, you can run IPv6 over it. You don't have to invent all kinds of new NFC-specific protocols. You can just run IPv6 over it. Okay, any questions at this point about 6LoWPAN? Yes?
If you would have to give one example where you believe this is a great example of an implementation, an IoT implementation, using one of those standards, which would you give? Is it in a university? Do we have any commercial applications?
Well, there are lots of things out there where you have to look under the hood to find out their 6LoWPAN. So if you look at the Gigaset Elements product,
Siemens?
well, Siemens has spun that off. Gigaset used to be a Siemens product, there is now a company called Gigaset. And they have a DECT-based product that is doing things in the home automation space, including alarming. That's internally 6LoWPAN. But they don't talk about it. They just use the technology because it's out there. And there are lots of examples like this. There is, right now, I don't think, a flagship 6LoWPAN application that everybody would like to point to and be happy about. There are lots of things happening. Okay, so let's look at the next part, still at layer 3, routing. Of course, we need to be able to find those paths. How does packet coming in here to the edge router actually find the path down to the host? Now, one important thing to keep in mind is that it's easy to forget if you come out of the sensor network space. In IP, not every node needs to be a router. We have the host router interface. And what 6LoWPAN ND gives you is a way of, for a node to attach to a router and use the routing capability of that router. Of course, we do that all the time, but when we open our laptop, we don't run the routing protocol there, but we talk to a base station and that talks to a router somewhere that runs the routing protocol. So not everybody needs to do this routing thing. But if you want to do routing, there's a whole lot of protocols you can choose from, including a large number of protocols defined in the domain space, like AUDV and OSLR v2 and so on. So there are lots of things to choose from. But there's also a protocol that was designed specifically for this space. It's based on the connection tree protocol. It's essentially assuming there is one more powerful node, and that is pretty much the edge router and different channels. And this spans a tree, or actually a directed acyclic graph, because a tree has this problem that you only have one parent, and it's much better to have multiple parents. So we build this tree. We have redundancies in there, so we can do a switch over to a different path without having to initiate rerouting. And we have a simple loop avoidance scheme based on assigning rank numbers. Now, when this was defined, people couldn't quite decide whether they wanted to have distributed knowledge about the structure of the network or just centralize it in the root. So there was this, they defined a storing mode where every router has a map of their subtree or their subDAG, and a non-storing mode where only the root has that map. Storing mode is pretty much dead, I would say, so non-storing mode is the only thing that's really out there in commercial use. The problem here simply is that when you join the network as a router, you have no idea whether you will get a subtree with 3 nodes or 3,000 nodes. So how do you size the amount of space you make available for storage? And if you only have 16 kilobytes of RAM, half of which is taken up by the operating system, and 80% of the rest is taken up by your application, you care about the size of your routing table. So that's a big problem. Nobody knows how to make storing mode networks work that are larger than maybe 30 nodes. So people have been doing this non-storing mode. And the disadvantage, of course, is if this guy doesn't know that this guy is in a subtree, it actually has to send the packet all the way up to the root, which then can source route it down to the right place in the network. So it's slightly less efficient for in-tree communication, but for everything that goes out or goes into the networks, or in particular for the device-to-cloud applications that people love so much these days, Ripple is actually very efficient and people like it. So the interesting thing about Ripple is it wasn't defined as a part of 6LoWPAN, but it's really an IP layer routing protocol. So we can put in other segments, so segments that don't use 6LoWPAN, and route over them, like over 6LoWPAN segments. So we can include Wi-Fi, Ethernet, maybe power line, and so on into the structures. That's pretty much a theoretical advantage. I haven't seen anyone actually use that, but it's there for people who want to use it. So within the theme, what have we learned? Here again, the idea was to use the less constrained nodes we have and move things that are too hard to do for a basic constraint node out there. So the LBR, which is the edge router role in Ripple terminology, that is the root of the directed acyclic graph. That actually keeps a map, and it's the only one who keeps a map. So there is the LBR is the only device that needs to scale with the size of the network. Right now, LBRs typically are Linux-based systems that have lots of RAM, so it's not a problem at all to do this. So it's a good idea to move this there. And again, contrast this with storing mode, where every node might find themselves in the situation that they have a large subnetwork and have to use up space. Okay, that was the network layer. Let's talk about applications for a moment. When you are developing a new application for the internet in 2014, or maybe in 2009, or 2004, you are not developing a new protocol. What you are doing is you're using HTTP and make your application work on HTTP. So HTTP has become the application protocol, except for very few cases where HTTP really isn't that good a fit. Many things on the internet use HTTP today to do the application work. And when you look at the things that need to be done in the Internet of Things, very many of those things actually fit with the HTTP model as well. So the first thing we looked at was, can we remove some of the baggage of HTTP? And the first thing that comes to mind when you look at HTTP is 500 bytes of HTTP requests to get a single data item. That doesn't make sense. So we looked at compressing HTTP. Yes, it can be done, it saves some bytes. Also has security problems, but we didn't know that at the time. But really the problem is all the complexity is still there. We have reduced the transmission cost of the complexity, but the implementation cost of the complexity is still there. And all the baggage, all the, in HTTP 1.0 it was Pragma, and now it's cache control, and all this stuff is still there. So you still have to implement it. And also there's TCP below. TCP almost vanishes in size under HTTP, but it's still another thing that you actually have to do. And then you have to do the compression, which also is not too light on the CPU, both in terms of energy and in terms of space needed to do this. And finally, compression only takes you so far, so you cannot really get that much out of compression. So we decided not to do that, but instead to do something simple. Why does HTTP have to be so complicated for the relatively simple transactions that we want to do in the Internet of Things? And well, other people say just send the data over UDP. That's going to work. And actually, it powers quite a few early Internet of Things applications. They just send stuff over UDP, encode it in some way, and it kind of works. But that ignores that there are some things that application developers consistently get wrong, like handling errors, handling packet losses, doing congestion control, and so on. We want to make sure that we have an application protocol that does those things, so the application developer can focus on the application. So not simpler, not just UDP, but as simple as possible, and what we got out of this is the constrained application protocol. So if you know HTTP, you probably already know 85% of what you need to know about CoAP, and Matthias is going to show you the other 15% the day after tomorrow. It's a simple protocol, it's datagram only, based on UDP, or if you need security, we are not using TLS with HTTP, but GTLS, the datagram version of TLS. We have a 4-byte header, and because we are not bound by the backwards compatibility issues of HTTP, we also could add an event model, actually an observation model, which can be used for notifying clients about changes at the server. So the examples I have here are going to look very boring for you because they look like HTTP examples. Well, maybe one packet format, which shows this stuff is real, and it's a 4-byte header here. There are some options and some payload data, which by the way is in CBOR here. And the point is that this interchange actually does exactly the same thing that an HTTP interchange would do. And since HTTP is designed to allow proxies, we can go ahead and build cross-protocol proxies that talk CoAP on one end and HTTP on the other end. So this is a very, very simple way of combining HTTP and CoAP into a system without one node necessarily knowing that this is being done to it. So this server here has to have no idea whatsoever that it's being accessed to CoAP. There is a website about CoAP. .technology is one of those new top-level domains. So .technology is actually a DNS name now. So if you want to see a little bit more about CoAP and how it's implemented, you can go there. So I would like to do another QA. Not here. I have to ask the organizers how much time do I have? till the end of the QA session. 10 minutes more, okay. So use 2 minutes of that for, yes.
Please come back to a slide.
This one?
I think it's one. What does it mean? I mean, what's the difference between exactly? I mean, how these HTTP and Quark coexist?
What's the difference between how they coexist?
Yeah, actually, I'm just getting confused about what's the difference exactly between Quark and HTTP.
Well, HTTP is a protocol that runs over TCP and that has expansive headers, text-based, and so on, and implements semantics like get, push, post, delete.
Okay.
And CoAP is a protocol that runs over Unity, uses binary encoded headers, has fewer alternatives for doing the same thing because we didn't have the backwards compatibility. But in the end, it implements get, push, post, delete. So that's why it's so easy for a proxy to actually translate between the two, because the semantics is very much the same.
Yes, it's still about the proxy. As you said, they map pretty easy, the mapping between HTTP and CoAP. But as I said, the observe option, this event model, is not in HTTP, but it's in CoAP. So what might be confusing that sometimes you want to achieve that kind of event model kind of communication, but how can you really map it into some HTTP client who's not aware of that? Or exploit that kind of feature, like it is supposed to be like a continuous polling.
Yeah, actually, it's not like HTTP cannot do that. It's that there are 10 different ways to do it in HTTP. So instead of having a single architecture like observed on the CoAP side, the proxy has a lot of ways to make the observed information available to its HTTP clients. So in the simplest case, it will just use the observed data, put it into its proxy cache, and the next time a client asks for the value over HTTP, it will get the new value. That's the simplest.
Okay, so the HTTP client is supposed to poll for the data. It's never.
No, that's not what I'm saying. What I'm saying is there are 10 ways of doing it on the HTTP side, and all of them can be implemented in the proxy if you need them. But we cannot help you with this HTTP side problem, that there are so many ways of doing it. So whatever works well in your proxy environment, use Apple push notification service. That's what one of my students did. It works very, very well. But of course, it only works for certain applications. So there are many ways of doing it, and it's the job of the proxy to translate the common single observed architecture into whatever works on the big web. Okay, I have 3 minutes for the next 50 slides. So maybe I'll do this in a somewhat cursory way here. Management. We have to manage those devices. There are IETF ways of doing that. The problem we have right now is simply that the IETF is in a transition from a simple management scheme, SNMP, which even has a symbol in its name, SNMP, to a rather complex mechanism based on game models and netconf protocol and so on. And we are a bit reluctant to follow that. So let me just say, management is something that is not yet defined in the IETF. If you need management, go to IMA, which has the lightweight M2M device management mechanism. We can do management for now, but we don't have the big architecture for doing it. That will require some more work. Security. As I said, security is not optional. And when designing CoAP, we actually decided we want to have very good security, real 128-bit security, which in RSA terms would be a 3072-bit security. So we finally bit the bullet and embraced ECC, elliptic curve. We now have a standard curve, the P256. Not everybody is absolutely happy with that after the Snowden revelations, but I think we are on the safe side here. So we know how to do the mechanics. And now the next thing we have to find out is how to actually do the workflow. How do keys go to a specific place and do what we need to. But on the protocol side, it's pretty clear we are running code over PTLS. And that's very different from the IoT security that you find in other places today, where you essentially just have a very thin perimeter protection. Everybody who knows the Wi-Fi password of your home has full access to everything that's in there, including all your pictures and your TV and whatever. There is no authorization in today's environments, and well, if you have kids, you know that this doesn't work. You need authorization even with a family. So, yeah, that's something we're working on. There's a working group called ACE, Authorization for Constrained Environments, and this is addressing this issue. So, in the general case, when we have two Internet of Things devices, and one is requesting a resource from the other device, in the end, these devices have to make decisions based on what some owners wanted the device to do. So if this is electricity meter and this is Google something, then the owner of that house actually, becomes more complicated, sorry, I took the wrong example, but anyway, the owner of that device has to decide, yes, you are allowed to make access. And there's a lot of business logic coming in. And according to the theme that we want to make use of less constrained nodes, it's probably not a good idea to just say C and IS are doing that on their own. So in our model, we just go ahead and say we define two additional roles which may be integrated. If you have a big device, like a home gateway or so on, it may be integrated, but it may also be separate. So the temperature sensor in my bathroom probably doesn't have all this functionality for running the OAuth protocol with Google or something like that. So some other device can do that and relay the results of that work down to the specific one. This is the way we can do real hard security on $5 devices by doing the complicated stuff, the business logic stuff on different devices, which might be your smartphones, your home gateways. So the really constrained devices in those cases only need to run very, very simple protocols. These can be based on symmetric cryptography, so your processing requirements can be very limited. And actually, we have a demo version of such a protocol called decaf. So look up decaf without the first E, and that is a proposal of doing that with a symmetric crypto environment. Now, this addresses a view where we already have established who are the owners for the device, and we just need to propagate their decisions down to the device. Actually, it's more complicated because devices may go through some life cycle. So they are manufactured, they are installed, they are commissioned, which may be at a different point in time than the installation. Actually, the commissioning may be before the installation. There is some bootstrapping going on. The application actually gets running. Maybe we have a software update that also changes some aspects of the authorization. So we have to reconfigure the application. We have to decommission devices. When you throw a light bulb into the trash, normally you don't think about whether you are giving somebody diving into your trash access to your home network. In the future, you will have to worry about it. And this is the decommissioning aspect. And maybe actually we even reuse things. So we are not throwing the light bulb into the trash, but we're using reusing some component, or we are selling the house, and so on. So there are lots of security events in the life cycle of a device that we need to know how to handle. And it's not sufficient to just think about the simple case. You actually have to have this whole life cycle and have answers. Of course, you don't have to define elements in the standards for every single of those transitions. Okay, so much about security. Let me quickly talk about data formats. So above the application layer, of course, we have some actual data we want to carry around. And right now, up to last year, the situation was we have some pretty nice data formats like XML and JSON. These are character-based, and they're kind of heavy for a constrained device. So it would be nice to have a concise binary version. XML actually has that, which is called XC. It's relatively complicated, but it can do. But there was a big gap here until last year, and I would just like to point out that gap no longer exists. There is a concise binary object representation. You can think about it as a binary JSON. It's not exactly that. It's solving a few more problems. But it's solving that with a view to the 40 years we have been trying to do that. There is an RFC 713 from 1978, I think, that almost solved the problem. And, well, other people have tried solving it, and yeah, I think we are pretty close with this now. So this is CBOR, concise binary object representation. There is a playground available, cbor.me, where you can write stuff in a JSON-like syntax and look at what CBOR makes out of it. And there is again one of those overview sites. This time it's not .technology, but .io, cbor.io, that shows pointers to implementations and so on. This is a year old, so it's not like completely developed in all parts of the world. Not everybody has an implementation yet, and so on. But it's a nice data format to have available. JSON is too big for. Okay, I think we have the final QA segment here. Yes.
One question. Sensor web from OGC. Is this something useful?
I don't even know what that is.
You don't know what that is?
No.
Yeah, so OGC stands for Open Geospatial Consortium, and they came up with a way to query sensors. You can register to an alert from a sensor, and it's called Sensor Web. And it's one of the, yeah, it's not IT yet, but it's a standard. So I guess if you have never heard about it, it's going to be difficult.
Right. So there are many standards in this space because it's very obvious that something needs to be done. And of course, many organizations have part of the puzzle. So if IoT is an elephant, somebody is holding the tail, and somebody is holding the trunk, and somebody is holding the leg. And many people are actually defining standards based on the part of the elephant they're holding. And I haven't looked at the OGC stuff. I looked at earlier OGC stuff, and that looked very much like tail-oriented design to me.
Maybe I have some comment on this. So I was in contact with some people there, the principal engineer, for instance. So the whole thing, it's a huge spec. So it's again something like what you have with Bluetooth back then. Nobody reads this because there's so much in it that you don't need. Nice part about sensor web is that they really specify how to get correct measurements. So the sensing part, that's very well specified in there. But then how to propagate that, how to send it to your application and so on, that's not very well covered in there. And they have some ideas to maybe split it up and take the good parts and combine it with something that is happening at IETF. but it's something valuable. You need it if you really do telemetry and need, have knowledge about the sensors. What does the sensor value actually mean? In what context was it taken? What can I calculate it from it? That's very good. But they have an old-fashioned way, let's say, how they do it. It's not very modular, and that's what has to change, I think. And they are aware of it, but it takes time.
There are several sensor-oriented specifications. There's an IEEE P15, I forget the number, that also has a lot of sensor-oriented things that are really useful to look at. So at some point somebody will have to sit down and take this space and look what's there and how things fit together. But most of these people make the mistake of actually trying to specify the rest of the architecture as well, so they have something that can be used as a vertical stack. And in those parts they don't know anything about, they often make very, very bad mistakes. So data formats for sensing are really an interesting question. There is one IETF proposal which is called SenML, Sensor Markup Language, because it started as an XML dialect. It now also has a JSON variant, and they are trying to pick up some of those things, also some UN specifications for universal methods of measurement and so on. And I'm sure physicists and other people will get together and do something in this space. So look at SenML for a comparison. Yes?
The important thing I can notice from today's talk is that in the state-of-the-art IoT network, we can say, we better assume that we have one or more nodes that are less constrained. So my question is, do you think the classical sensor networks, what was described before, the really ad hoc networks without infrastructure, because if we say that there is another type of nodes, it is infrastructure. So the networks without infrastructure, if we have homogeneous type of nodes, all nodes are the same, with the same power, with the same power of calculation, is it possible that this kind of networks will survive, we can say, or it is just inefficient? Because there is sometimes the applications, like in the nature, there is some for the animals surviving, or in the forest, we cannot really use the...
I didn't talk about that area, which we call challenge networks, where you cannot assume to have connectivity and you cannot assume to get it on demand. So that's a completely different issue. The IETF has been working on that for a while, and actually there is no work on a new working group to get these challenge networks, get the standards, the bundle protocol, and all stuff going on and make it into real standards. But on the internet, once you are on the internet, there is no homogeneous network, because there's always Google, and they have an acre of silicon in each of their data centers, and that's not homogeneous with what you do. And you might want to use it. So I think the model that we have constrained nodes and less constrained nodes, and those work together in some form, that's actually very useful.
Okay, so the future is heterogeneous network.
Yes, depending on your definition of heterogeneous. The nodes are going to be heterogeneous. The internet protocol, I hope, will be the same everywhere.
Okay, thank you.
Yes.
I mean, taking into account all of this, what was said, all of the categories of internet-connected objects, all of the protocols that we spoke about today, and the other protocols. We have some publish-subscribe protocols for the application layer, like MQTT. Can we have an architecture for IoT at large, not a scenario-specific architecture, for example, for a smart home? Can we have at least a pattern if one wants to design an architecture?
the IETF, I'm not the IETF, but I think a lot like the IETF. The IETF is a bit skeptical about architectures. So the IETF tries to build protocols. And one of the interesting things about protocols is we have an architecture in mind when we build the protocol, but we almost immediately find out that the architecture in which they are actually being used is going to be a bit different. So the architecture changes faster than the underlying protocols. And all you can hope for is when you build the protocols that you are versatile enough to cover a number of progressing architectures for a period of time. That would be designed for decades. So I'm very wary of somebody making a nice architecture diagram and saying that's how things work together. Because there's always something that specific use case uses that doesn't fit into that picture, needs another protocol, needs another device, and so on. So the short answer is no, I don't think there is such an architecture.
Right. Okay.
Yes.
Yeah, in the future, the vehicle, the car, it will be carried with many sensors, and hundreds of sensors in one car. And the sensors in the vehicle, the battery is unlimited, and the computation power is also unlimited. Because with the car, you can have many powers supplied by the vehicle engine, right? So is there any IETF protocol for the vehicle communication?
Right now, there is no working group specifically chartered to do that. There is a group of people who are looking at the ITS space, the Intelligent Transport System space, and the protocols coming out of that, but that hasn't led to a working group being chartered yet. And there are lots of people looking at car-to-car, and it's kind of pretty close club, and it's really hard for somebody like the IETF to crack that club. I wouldn't agree with the assumption that power is unlimited in a car, because if you have something like 300 or 700 CPUs in a car, then at some point that car is going to melt if each of them uses too much power. So even there, you have to think about power, but it's not like a battery, AA battery powered device that sits on a wall and has to work for 2 years. Yeah, so that's certainly true. Yes.
Yes. In the first part of your lecture, you introduced the classification of devices, class 0, class 1, class 2. Today there are still some technologies that, like RFID or some reading system, which are not able to implement also lightweight IPv6 protocol. What is your idea to include these smart devices? And IETF has been working on this field using, for example, gateway or also other proxy.
The IETF has tried to address the RFID space. That also turned out to be a bit difficult not to crack. This is also a pretty closed club, and it's hard to get in there. But I think it's important to remember that RFID really is about nodes that are not becoming part of the internet. So the old Internet of Things argument that these devices somehow are digital and can be part of the internet, that's just not true. They are not communicating like that. However, there are things like NFC, which are using closely related technologies. And for NFC, I had an example of somebody actually cooking up a way to do 6LoWPAN over NFC. I think we are going to see things like that. We are using devices that are powered by some reader device and becoming internet nodes for the short duration they are powered. We're going to see that more often. So that takes away the problem. Right now we have the problem that the reader device, to a large extent, has to understand the application enough to interact with the RFID device. So for a tagging application that is trivial, but if you think about things like door locks and so on, it becomes a bit complicated. And putting a door lock, for instance, on the internet for a short time, somebody is accessing it using a less constrained device. That's a pretty interesting idea. People are building businesses around this interesting. So I think there will be some merging going on, but the RFID tag on my glass of jam is probably not going to join the internet for foreseeable. Like a barcode join the internet. Are we done with questions? Okay, thank you. Those were really good questions.